Now, yesterday we talked about two important concepts involving this del operator. Okay, so the del operator is up the top. It's got this ddx, ddy, ddz type vector. And the first idea we talked about was divergence. Okay, so you've got something like a vector field. So, you know, x squared minus y times I, y plus zj, z squared minus zk, right? And to compute what we call the divergence, we apply this del operator through a dot product. Okay, it's not really a product. Okay, and so just to refresh our memory, that operates on that, that operates on that, and this one operates on that, and you add them together. Okay, so you get something that's not a vector, it's just a function or a number or something like that. Okay, and then we talked about what does it mean. Okay, so the divergence of a vector field, it measures the tendency, the tendency of the field, let's say it's a velocity field, to spread, okay, to expand. Okay? If the divergence is 0, then, and we're associated with a fluid, we would say that the vector field is, or the fluid is incompressible. Okay? All right, that's the first one. The second one that we looked at was curl. Okay? So curl is the other way of combining sort of vectors that you learnt about in first year, and it involves a cross product. So that X symbol, the cross product. Okay? And so the way that I usually do it is if I'm doing it by hand, I set up a 3x3 determinant and I just expand it along the top row. Okay? So the answer you get here is a vector, right? So in this case we got the, you know, this thing here. Negative I plus j plus k. Okay? So our answer is not a number, like it was for the divergence, it is a vector. And then I set up a little paddle wheel kind of problem, and I drew parts of the vector field, and we were looking for rotation in that paddle wheel about its sort of center point or its center axis. Okay, so the way that I try to remember curl, apart from the computation, is that it's got to do with the tendency to rotate or rotate things. Okay? All right. So curl measures rotation, divergence measures expansion or spread or something like that. When we talk about scalar curl, we're talking about the k component of that vector. Okay, so if I go back to my previous example, in the second one, so that was our vector field. We computed the curl, we got that. It's just that number or whatever that expression is, right? That would be called the scalar curl. Okay? All right. The last thing we talked about yesterday was line integrals. And line integrals are new for probably all of us, but we know how to integrate from high school. Yep. So at high school, we were integrating over intervals, like in the top right-hand corner. So we'd integrate from, I don't know, x equals a to x equals b, and you'd have this sort of expression. And you could think about area under the curve, stuff like that. Yeah? So here what we're doing is we're integrating not over intervals, but curvy lines, or line segments. Okay? They may not be straight, and they may be, very difficult, but that's what we're going to look at. And part of the motivation here is to look at more complicated problems from, calculating work and moving things around and stuff like that. Okay, so the example I looked at was this one and this one. The first one doesn't involve a vector or a vector field. Okay, it doesn't involve a vector field. So it's just a surface. And let me show you a picture from yesterday, just to refresh our memory. Okay. Here's the surface. We're integrating around a circle in the xy plane. So in 3D, that'll be a cylinder. Right? They're going to intersect along that sort of oval or ellipse. And essentially, instead of integrating over an interval, we're integrating over this, circle in the xy plane. So it's a curved kind of thing, right? You can relate it to area. Under that curve looks like a fingernail, right? And so how do you do it? We need a definition. This is the definition that we used. Okay, so what's R here? R is a way of describing the curve that you're integrating over. Okay, so here it's a unit circle. It's a pretty easy parameterization. Say x equals cos t, y equals sine t. That's pretty easy. And you multiply that with the length of the tangent vector. Okay, so you've got that bit, that's f along your parameterization or along your curve, multiply by the length of the tangent vector, and you integrate in the normal way. Okay, just high school, regular Riemann integral. Great. The second integral we looked at was what's called, I guess, a vector line integral, or it uses a vector field. Here, we don't start with a function like this, we start with a vector field. Okay, same curve, but a slightly different way. Instead of having, just scalar things multiplied together, you've got a dot product. A dot product, okay? So that's a vector, you dot them together and you integrate. Right? So again, it goes back to something that you know. Both of the answers are numbers, right? I think we got 2 pi for the other one, which is fine. It's not clear what this means. The above one is area, but we're not sure what this means. Okay? But we'll work it out in a minute. Okay. So let's delve into this a bit more. Let's delve into this a bit more. Just give me a sec. Aha. All right. So let's have a look at this bigger picture. We've done a couple of examples yesterday. Sometimes in my notation, I use 2 vertical lines. So what, basically here, it's the same as this. Sometimes I switch between the notations. Okay, you see this in first year, this is seen other places, but it's the same thing. So it's the length, right? So somebody asked at the end of the lecture, okay, Chris, this looks fine, but what is this? And I said, I'll talk about it today. Okay, so let's talk about it. Let's look at that second thing. T hat is a unit tangent vector in the direction of motion. So there's a couple of things going on there. tangent to the curve, length is 1, and what's the direction of motion? Okay, so these are quite big questions, and they can alter the problem. So let's discuss that a little bit. If I have a curve here, right, this circle, let's just reread the question. My vector field is that C, the curve, is oriented by an anti-clockwise rotation. An anti-clockwise rotation. So that sort of gives us a little idea of direction now. You come back. All right? So, anti-clockwise. So we'd start here, t equals 0, and as t increases, we would go in an anti-clockwise direction. Okay? So let's talk about that a bit more. Let's say I have a curve. There's two ways to move around that curve. From, say, A to B, or from B to A. So you go this way, or you go this way. There's two ways. Yeah? So you need to know, if you're going to have a tangent vector, you need to know which way the tangent vector should be pointing. Right? So this is a bit more difficult than what you see at school. Yeah? It's not just a tangent line and the slope of a tangent line. Here you've got the direction as well. Okay? So it could be pointing the way that I've drawn it, or it could be pointing in the opposite direction. Right? So, which one is it? Which one is it? So it could be pointing that way, or it could be pointing that way. Which one? We don't know. So we need a sense of direction. Yeah? Okay, you're looking very sleepy, man. Is everything okay? Okay, good. Just saying, if you're here, try to stay awake. Okay, so which one do we want? Do we want that way or the opposite way? The question tells us. Okay? The question tells us with the orientation or the direction. Okay? So, that's one thing. Now let's look at this one. How do we compute a tangent vector? If I've got a way of describing my curve, what can we do to R to compute a tangent vector?
Dot product is 0? No.
No, from a calculus point of view.
Just like the gradient?
Almost. You're on the right track. So if I've got, let's go back to what we did over here, right? If I've got my R vector there, how can I compute a tangent vector using calculus? Using vector calculus. Sort of, but not quite. You said that too, right? Any ideas? It's simpler than you think. Yeah, no, dot product, no. Yeah. So any ideas? Yeah, the derivative of R. So R's a vector function of one variable, t. So if we wanted to compute a tangent vector, we would just differentiate. Okay? But that may or may not be unit length. So to find a unit tangent, we would just divide by the length of R dash. Okay? right? So one way of putting this together, as long as it's not 0, something like this. Okay? All right. So now we've got this mess. How does it sort of work with this? Well, let's look at the dot, and now we're getting back to your dot product. Okay? Now we're getting back to your dot product. Let's look at this dot product here. Okay? So let's think about that. Okay, so if I'm integrating this bad boy here, similar to this, I'd multiply by the length of the derivative. Okay, and you can see, hopefully, boom. As long as the derivative is not 0, the 0 vector, we can do that and we get the expression that we had before. Okay, so from a computational point of view, that's super important. I'm just sort of telling you where it comes from. So if I was, have I got this? If I was computing this, I would go something like this. Okay? So from a conceptual point of view, that's where the bottom bit comes in handy. From a computational point of view, when you're actually doing the problems, it's the top one that's important on the right. Okay? So, but let's actually do a little bit more digging and see what we're actually computing here. Okay? So let me draw another curve. Okay, let's say that's a C curve, whatever. We're going to integrate over that curve. Okay? And at that point on C, let's say that's your vector from your vector field. Okay, let's draw in a unit tangent, which we can compute, but I'll just draw it in. Okay, now what is F dotted with T hat? We're getting 1131 vibes here now. F dotted with T hat geometrically. Can anyone remember that from first year? Yeah, you're on the right track, right? Is that what you're going to say? Yeah, so you can think about drawing a little right angle triangle, and then you can say, okay, well, this is the component of F in the direction of the tangent vector, right? So we're actually integrating that piece around the curve. Okay? Yes?
Don't you have to divide it by the unit length?
Yeah, I'm saying that it's unit, right?
Oh.
Yeah. So see the T hat? Yeah. Okay? Now, but there's also another thing going on here. There's also another thing going on. When we're doing these problems, we get an answer, a number, right? We're kind of measuring how closely F lines up with the tangent vector, or the curve itself. Okay? If you get a large number when you're doing an integral like this, it means you have good alignment between the vector field and the tangent to the curve. Right? They're sort of pushing in the same direction, or sort of the same direction like we have in the picture. Okay? If you get something that's larger negative, sort of the vector field's almost pointing in the opposite way, sort of impeding the movement or something like that. Okay? So it's a little bit conceptual. It's pretty easy to compute as long as you don't make a mistake. But that's a short justification on sort of how we come up with the, where are you? With sort of this thing, for example, right? I just think of that, oh, well, you're taking the dot product with the tangent vector, unit tangent, and you're integrating. Okay? Questions? Let's have a look at home. What's going on? Anyone awake? Ooh, 20 people. I'm going to be late, but I'm on my way. Okay, awesome. Differentiate RT. Let's put that up, because that's a good answer. Yeah. Okay, so to form you've got a curve, you've described it using R of t vector. To form a tangent vector, differentiate it. Okay. Now a couple of things. I can never find these things when I want them. Aha. Let's have a look at part B again. Yep. So we're integrating in an anti-clockwise direction around a circle. Okay? And I got an answer of 2 pi. Now, what happens if I changed from anti-clockwise to clockwise? Would that change our answer for part B? Yeah? How would it change it? Negative. It'll be the negative, right? So you can kind of justify that by thinking, well, if the tangent vector points in one direction for the first problem, it'll point in the sort of the opposite direction for the other problem. So you have a negative sign associated with it. So that sort of implies that you won't get 2 pi, you'll get negative 2 pi, right? You with me? Yeah. So direction matters. And if you're doing problems like this in Mobius, and you're not sure, just think about the signs of your answer, okay? Think about the signs of your answer. Questions? So there are quite a few questions in lab test 1 of this sort of style. So let's sort of dig deeper, and we'll do a few more. Let's look at this one. Okay? This sort of brings everything together in some sense. So let me... Whoop. Yeah. Okay, more on line integrals. So here you've got 2 questions. One involves divergence and curl. Great, no problem. The second one is a little bit more difficult. The line integral of f along the straight line from point A to point B. So this is different now because it's not a circle, it's a line segment, and you have to come up with a parameterization. You have some way of describing the line. Okay, so let's do the easy part first. So remember that we've got a del operator, and it's defined using these partial derivative type operators. And for the first one, it's the divergence, dot product. Yeah? So, I'll write it as a row without the i's, j's, k's. Okay, so pretty easy for this one. You just expand it in a component-wise fashion, right? So d dx of 8e to the negative x, d dy of cosh z, d dz of negative y squared. Okay? So pretty easy. So that one on that one, that one on that one, that one on that one. So only one of this is going to give us a non-zero answer, right? So it's going to be something like negative 8e to the negative x. Okay? It's a number. It's going to be negative. So we're going to have net inflow. Okay? But let's move to curl. Okay, curl. I do them as determinants, but you can do them any way you like. Okay, so just remember the way I do it, I start on the top row and I expand along the top row, top left-hand corner. So IJK, and then I just play a game of cover up. So what are we going to get? So for I, it's I times the determinant of what's left. So when I differentiate, I'm going to get negative 2y minus shine z. Okay, move on to J, I change the sign, I do my cover-ups again. Okay, J, d dx of that minus d dz of that, well, that's going to be 0. And finally, d dx of that, d dy of that, 0. Okay? So it'll be something like this. Just writing it as a column. Okay, so that's the computational part. I guess you just need to be careful you don't make a mistake. You need to be careful with the signs. You alternate the signs on the ij's k, so positive I, negative j, positive k. All right, so now it gets a little bit more interesting. With part 2, you've got a line integral and the segment is sort of sitting in three-dimensional space. How do we do that? Okay, so the first thing that I usually do with these problems is I draw a little picture. Okay, the picture doesn't have to be accurate, but let's just see. Okay, so I've got 2 points, A and B. I don't draw in the axes, so that's going to be A, that's going to be B. Okay? And I'll draw in the origin. Okay, back to 1131, math 1131. For me, line segments, you just got to get onto the line segment and then you use a parameter to move around. Okay, it's like the vector parametric form of a line. People are going, don't take me back there. Don't take me back to first year. Right? So, if this is the origin, and I know the point A, what vector takes me from the origin onto the line? Morning, you made it. Well done. What vector takes me from the origin onto the line?
Vector A.
Aha, the vector OA. Right? Yeah. So let's get on there. Let's get on this train. Boom. Okay. Now I'm on the track or the line segment. I want to move around. Okay. So let's say I want to get here. How can I get from A to P? Any ideas? Yes. Hang on. Just for the 20 people at home.
I don't know if this is the right order, but you could project OA on AB, the negative.
You're on the right track with AB. Something to do with AB. Yeah, maybe. Yeah, half. Someone had their hand up over here. Yeah. So you're almost there. Projection, I think, is a little bit over the top, but the AB vector is important.
From point A, you add a scalar times AB.
Yeah. That's it. Is that what you were going to say? Yeah, that's it. So let's say I want to get, so I'm already here. Let's say I want to get to here, right? So I don't want the whole of AB. All I want is like, I don't know, half or something, right? So to move anywhere on that point, on that line segment, you can go, oh, I'll just take a multiple of AB. Yeah? So really, what's happening here is something like that. Okay, now let's check that the orientation or the direction's right. Okay, we want to go from this point to this point. Okay, so when t equals 0, we get there, right? Because it's just OP, this thing is just this disappears, right? OA. And then as t increases, we get all the way to B. Okay? So that's a real simple way of describing this line segment using first year Math 1131. Okay? Questions? Yes, some people ask, oh, that's too much work. Can't you just give me the parameterization? Sometimes the questions do. Sometimes they do.
I gotta be honest, I was lost. What were you doing here?
So what are you doing here? We're trying to describe the points on the line segment AB. Yeah. It's okay. Just 1131. It's all right. It's early still, don't worry. Other questions? All right, let's have a look at home, see if anyone's piped up at home. Yeah. Oh, so we could even add another one in, right? So let's add another line in. OP is OA plus AP. Oh my goodness. Yeah, you rule. Zach, you rule. Okay? So that is an example of a line segment where you have to, describe it somehow. Now, is this the only way of describing the line segment from A to B? Can anyone think of another way of describing it? Using a parameter t or lambda or something? I think in first you did lambdas, right? Do you think there's more than one way of describing it? Yes. There are an infinite number of ways. Okay? So you may be doing something, right? Your friend may be doing something, and you're like, hang on, this is my description, and this is my description. They're different, but they can still be correct. Okay? Usually, because I'm a simple man, I go for the most simple ones possible. Okay? But if you want to get fancy, it's completely up to you. Okay? All right, so what will our vector R look like? Okay, so OA plus TAB. So OA is there. Okay, the vector from A to B. Can anyone remember how we do that? Vector between 2 points.
Wouldn't it just be subtract the first one from the second one?
So, yeah, so AB is going to be, so vector AB is going to be the vector OB minus the vector OA. Okay? So, T times AB, so it's basically that minus that. So log 2 minus 0, 1 minus 1, 2 minus 0. Okay? Now, for many people, that's actually the hardest part of setting up these problems. Because you have to think, okay, how am I going to describe this set of points or this curve or this line segment? Okay? The computation's not hard, but let's do it anyway. Okay? So, if that's my R of t, let's differentiate. So if we differentiate this, what's going to happen? Well, that'll just become a 1. The first part will disappear and I'll just get this constant vector. Okay, so I've got 2 important things so far. All right. Let's compute our vector field along our curve, C, and then we dot them together with the derivative. All right, so let's go back up here. Here's our vector field. We just basically replace x with 2 log 2, y with 1, and z with 2t. Okay, so let me write those out so it's clearer. Okay, so I've written out the components of the R vector there. All right, so let's go up there and say, okay, we're going to put in our values. All right, so instead of x, we put that in. Cosh z is going to be cosh of 2t. And negative y squared will just be negative 1. Okay, so this is our third bit of information. Okay, so now we combine them. We do the dot product of the 2 vectors down here, and we're going to integrate it with respect to t. From t equals 0 to t equals 1, because that's what maps out our little line, okay? So we're going sort of that way. Okay, so now we just want to do this dot product. It looks okay because there's a 0 there. Okay, so when we do that, we'll just multiply by log 2. That gives us 0, and then we'll get minus 2 on the other side. Oh, gosh, thank you. I missed the H. Who said that? Oh, 2 cosh t, right? Is it? No, it's fine. Yeah, cosh 2t. Is that what you were going to say? Who said that? Yeah? Thank you. Yeah, cosh, not cos. Yes, question.
I was just wondering where the 1, 0 on the limits of the interval came from?
So we've chosen it. So we could use any limits. But I just chose 0 and 1 here. Because, basically when t equals 0, I get OA. When t equals 1, I get OB. Okay? But if you don't want to use that interval from 0 to 1, you could use 0 to 2, 0 to 10. But you'd have to change your R of t vector. Okay? So it's up to you. All right, good question. All right, so we do the dot product. We get something like this. Okay, it looks a bit nasty, but it's not too bad because you see the log 2 at the front and then log 2 in the index. So you integrate that and you're done. Whew. So you can see they're not super difficult, but they are a bit longer because you have to do more things. You have to parameterize a curve. You have to describe a curve in the right direction. You have to compute the tangent vector, r dash, right? You have to do a dot product, and then you have to do an integration, okay? So it's a little bit more involved. Questions? But the good thing is it comes back to what you know from school, right? Like you should, from school, you should know, you should be comfortable with integrating something like that. If you can get to that, then you're in a happy place, hopefully. Okay? Okay, so let's try to put this in a bit of context and relate it with some sort of physical process. Okay, so suppose you're moving some mass from point A to point B, right? And F's the force. This is one way of calculating the work done, so in joules or something like that. Okay? Questions? Okay, so a little bit long, but as long as you keep track of everything, there's three important things: the parameterization, the derivative, and the f, and then you dot them together. Questions? So you might see something like this on lab test 1. So obviously navigating it, getting the time under control is important. Not making a mistake, also important. Remembering cos and cosh are different things, also important. Okay? All right. So this is just what I repeated before on the previous slide, so no need to go through that. But it's a good question, these kind of problems, right? When you're integrating something, think back to school. How would you... Okay, this is not a trick question. How would you integrate that top expression? What would you do? Okay, it's not a you guys doing noughts and crosses? Come on. At least pretend. Just pretend like you're paying attention. I know it's early. Come on, I see everything, man. Like that's the thing that students don't know. I see pretty much everything. You know, and I look as well. Like sometimes I'll make a game out of it. That's why I walk around, right? Because I'm like, so-and-so's got headphones in. So-and-so's doing noughts and crosses. Don't worry, somebody was watching porn in one of the lectures like a few years ago. He had his laptop up. He was looking really like engaged. I'm like, oh, that guy's feeling me. I'm like, no, he's not. He's doing something else. Yeah. It's unfortunately, it's a true story. All right, now back to the program. We'll get a break in a second. Oh, no. Oh, I can't remember. But it made the news, hey. It made the news. Yeah. I think it was probably someone set up, like someone's like filming. I'm like, this guy's watching porno. Yeah. Get that on TikTok immediately. All right, so back to the program just before we take a short break. How would you do the top integral? What would you do? Right? What's the thought process? Yeah, compute the antiderivative, right? So x squared becomes a third x cubed. And you evaluate it at the endpoints of the interval, x equals 1, x equals 0. Does anybody know what this is? This is the fundamental theorem of calculus, FTC. It means if you have an antiderivative, all you need is the endpoints, 0 and 1. Now, you use that for probably many years, right? At high school and in first year. Is there a fundamental theorem of line integrals? Yes, there is. Thank God. Right? Thank God. There is. Okay? Now, what do we mean when I say, I asked this in first year as well, what do we mean fundamental? What do we mean by the word fundamental? What does it mean to you? If I say something's fundamental, what do you think it means?
Very important.
Yeah, important, maybe on the exam, right? Some people think, oh, fundamental means easy, okay? It's exactly pretty much what you said and what you said, right? Fundamental means important in this context, not necessarily easy, and probably on the exam, okay? So, important. So if English is your second or third language, maybe you don't speak Australian. I speak perfect Australian, by the way. Fundamental and important, they're sort of transferred. Okay? But there's a couple of extra bits that we need. We can't necessarily do this thing that we did at the top all the time. Okay? There's a special quality of the vector field itself. Okay? And this is it. Now, you asked the other day about the connections between gradient, div, curl, del, all that sort of stuff, right? And I said, oh, look, we'll show you some connections. That's what we're going to do in the next hour. Okay? So, this is super important. Okay? So I'll unpack that in the next hour. Feel free to diverge from where you're sitting if you want to go sit up the back. Thank you for staying with me. And let's take a 10-minute break. So basically the f dot t hat.
Yeah.
So think about that. So what is a unit tangent vector?
Yeah.
Okay, well, a tangent vector is just the derivative.
And
To make it unit, you divide by the length.
Yeah.
So that times that. Okay, well there's your t
Tangent,
vector,
yeah.
right? And then to put it into the ds notation, where's that? Like the part A. Up here, you want to multiply by the length of the tangent vector. So it cancels out,
Right.
and then you're just left
And
with
then you're
that.
just left with that.
Yeah. So that's it.
Okay.
Mm.
That makes sense.
So you just got to think, oh, what is a tangent vector and how do I make it equal to 1? Oh, derivative, length. Easy. Cancellation.
Lovely. Thank you.
D.
Was a bit
You
embarrassed.
feel, you know, that's all right. You feel a bit more awake now?
I need to go get water.
Yeah, go.
but
Yeah,
like,
yeah. We'll wait for you.
What is R of t? That's what
It's a vector that takes you from the origin to the curve.
Oh, so is it just the t, or is it
Hang on,
different?
let me see. Let me see if I can draw something. Is there? Wait. So let's say you're in three-dimensional space, right? So, okay, so you get from the origin.
Oh, that's just
Yes, we know just that point in every point on the curve. So as t moves, that vector will move with it.
oh, so that's why. So
Well, that plus that. Yeah. Otherwise, it doesn't work. Otherwise, you're stuck at one point. Yeah.
so it's just like just going back to the vector stuff, but then this is a curve.
Yeah, exactly. So you want to move around the line. The T parameterization allows you to move around. You do that by stretching, compressing, flipping, whatever. So I had a look at your thing. Yeah, so, where is it? I've got it here somewhere.
I did do the quotient rule too.
Yeah, I flipped it around too.
Got the same answer.
Yeah.
Okay. 4.9.
So, why don't you take a photo?
Okay, thank you.
Hey, hello. What's up? Because we told y equals, so 0 plus t log 2 is x. 1 plus 0 times t is 1. Right? So just, no, plus. Plus, not equals. Okay? Plus. Not equals. Sorry, why did I write equals? Plus. Okay, so then it's, x is that plus t times that. Y is 1 plus 0 times t. Z is 0 plus t times 2.
Oh, okay.
Yeah, sorry, that's a plus, not an equals.
Okay. Thank you. Now, why is a zero? Is that B point B? This one is that point B.
That's a, so this is OA, and this vector is AB. Yeah?
Yeah.
T
Got it.
times AB. Yeah. It's a bit tricky, like, if you haven't done vectors for a while, it's a bit tricky. Hello? What's up? Oh, yeah. It should be plus. Yes.
I figured it out.
What are we doing wrong?
I just subbed like 0.09 straight in with that. No, thank you very much.
No worries. Yeah, so for everyone at home, you'll be able to hear me, right? So x is just the first bit of this mess. So 0 plus t times log 2, that's t log 2. Y is 1 plus t times 0. Z is 0 plus t times 2, 2t. Okay? Let me know if you got that at home. Okay, let's get back to it. Just a small correction. A small correction. So I think I had equals here. It should be plus. I mean, there's a plus there, so you'd expect a plus there. So just thank you for those people who asked about it. Oh. Okay, let's get back to it. So based on the really simple example at the top, can we do something like this for these new integrals that we've been looking at? Okay? Can we just sort of use the endpoints of the line or the curve or whatever instead of doing all the computations? And the answer is yes, if the vector field that we're integrating has a certain structure. Okay? It has a certain property. And the property is this. You're given a vector field, find a function phi such that when you take the gradient of phi, you get the vector field that you started with. Okay, let me say that again because that's a lot of information. You're given a vector field f, something, something, something. Can you find a function of, say, x, y, and z, phi, such that when you take the gradient of that phi, you get the original vector field? Okay? So let's try that. Let's try that. So remember, our del is defined as this. Yep. And so if we were computing grad phi, or grad f, whatever you want to call it, you take the partial derivatives and you write each of them as a part of a vector, right? Okay, so I'll come back to part one in a minute. The basic conclusion there, as we talked about yesterday, is that when the curl's zero, the zero vector, we call the original vector field irrotational. Irrotational. Okay? But number two is a bit more interesting. Let me just zoom in a bit. Okay? So let's think about okay, that's better. Okay, let's think about part two. Find a scalar field phi such that gradient of phi equals the original vector field. Okay, so what does that involve? Okay, well, we want d phi dx to be that mess. We want d phi dy to be that mess. And we want d phi dz to be that mess. If those three equations are satisfied, then we can find a phi, okay? So here's what we want to solve. D phi dx equals that. D phi dy equals x squared times z und d phi dz equals that. Okay? So we have our first set of partial differential equations here. I told you we'd look at partial differential equations. This is a sort of a simple version of them, okay? So what are you trying to solve here? We're trying to solve for phi, which is a function of x, y, and z, okay? All right. So how can we solve these three equations? Anybody know? What could we consider?
Just finding the antiderivative as we did before.
Yeah, integration seems like a good starting point, right? So if I integrate the first one with respect to x, what's going to happen? Well, that 2x is going to become x squared, and I imagine everything else is a constant. Oh, I'm going to integrate cos x as well, right? So that'll become sine x, that'll become x squared yz, and then I just need to think about a constant of some sort of constant of integration, okay? What about if I integrate the second part? So I'm integrating with respect to y now. What am I going to get? Yeah, we'll get something like y x squared z plus something else, right? Some constant, inverted commas. And what about this? Well, this will become x squared yz, this will become e to the z, and then something else. Okay? So let's do that and see what happens. So I'm going to integrate separately the first one with respect to x, the second one with respect to y, and the third one with respect to z. And this h1, it's going to be like a constant of integration that takes care of the other variables. Okay, integrate that. Same with h2. Integrate this with respect to z. Okay. So you can see we've got three expressions, and they're not necessarily the same. But are parts of them the same? The x squared yz is there in all of them, yeah? But what about the, oh, I've forgotten the e to the z. But what about the other bits? So when we integrate e to the z, it'll go down there. Thank you. Okay, so that bit's in all of them. There's a sine x there, there's no sine x there, there's no sine x there. There's an e to the z here, no e to the z there, and no e to the z there. So it's a game now of choosing h1, h2, and h3 so all the three parts are exactly the same. The three expressions for phi are exactly the same. Okay, so who can suggest what h2 might be? Or h1 or h3? Yes, we're doing a lot of heavy lifting today.
It would be sine x plus e to the power of z.
So if you look in the middle one here, we want that to capture this and that. So if h2 is sine x plus e to the z, h1's e to the z, h3's sine x, then all the three things align. Okay? So I would say this. Okay, so making those choices, we'll get something like this. Okay, now you can test that. You can take the gradient of this bottom thing and you end up, hopefully, with our f up the top. The vector field that we started with. But how does this help us? Okay, it's fun to solve partial differential equations, but actually, how does this help us? Well, what if I told you that this knowledge can greatly simplify the calculations in part 3? Okay? And in fact, the parameterization doesn't really care. I don't care what curve it is, I'm just worried about the endpoints. Okay? Just like when I did this thing, I only really cared about the x values at the endpoints of the interval, just 2 points. We're going to do the same thing here. Okay? So let me show you. Because f because f is the same as the gradient of something, it makes a huge difference in the calculations. Let me show you. Now, having this gradient here basically means the integral and the gradient kind of cancel out. Okay? I'll show you why that's true in a minute. Okay, so if we go back to our curve, if I just sub in t equals 0, I'll get 0, 1, 0. And at the other endpoint, t equals 2 pi. I'll get 0, 1, 2 pi. Okay, so that's what I'm talking about. I'm talking about the starting points and the ending points when I'm talking about B, the point B and the point A. Okay? So, what is phi of B? Well, x is 0, y is 1, x is 0, y is 1, z is 2 pi. So it's basically this. Okay, so you would take the values for A and B, put them in here, and you'll get a number. Okay, if you do that, that's what you'll get. Let me just zoom out a bit. Okay. So we didn't have to calculate anything to do with the curve, really, apart from the endpoints. We didn't have to compute a tangent vector. We didn't have to compute the length of anything, right? So this it can be a real time saver, okay? And so you should try to look to save time whenever you can with these line integral problems. A good question here, how did I know that I could solve these equations? Well, that's where the first part comes in. All irrotational fields, right, so you take the curl, you get 0, have this property. Okay, you can always find a phi such that grad phi equals the vector field. Okay? So the first thing is like a little test, a sufficient test. Right? The second thing, okay, if I do that, then I can apply this and just use this fundamental theorem or fundamental way of working. Okay, it's a good time saver. What else does it mean? It means that we don't really care about the curve anymore. We only care about the endpoints. Right? So if I, this curve here is a spring, right? It looks like it's a helix. Looks like a I don't know, a spring, right? But we don't care about what curve it is anymore. We just care about the value of the phi at the endpoints. So even if we went a different way, a different spring, a different curve, different line, we'd still get the same answer. Just let that sink in for a minute, right? That's a certain curve. We don't actually care about the curve anymore in this working. We just care about the starting point and the ending point. So you should get the same result no matter how the 2 points are connected. Okay? So it's independent, the result is independent of the curve, really. So you can go any way you like. Questions? That's pretty deep, right? It's pretty deep for a Wednesday morning. Yes. Hang on. For everyone at home. I know. It's important though.
You're using 2 pi and 0 as b and a, right? Yeah.
Well, as the t values that give you b, a and b, right? So when t equals 0, you sub it into r, and you get the vector OA. Yeah. Now, I want everyone to be heard in this class, right? It was funny. I think I was on Facebook the other day, and you know how people complain online? They'll go to somebody's page and they'll say, "I had a terrible experience with your company." Do you know this? Have you heard of this? Right? Or there'll be an ad. An ad will pop up in your feed for a bank or something, and it'll be like, "Yeah, this bank's excellent." And people say, "You're terrible. I had so many problems." Blah 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 blah. Right? Anyway, sometimes the companies respond to the people, and sometimes it's funny, but sometimes it's copy and paste, right? It's usually, "Oh, we really value you. Could you send us a private message," or something like that, right? So somebody replied to that and said, "Thank you for your copy-paste answer. It really feels like you're listening to me, right? I'm being heard." That's why I want that in this class. I want you guys to be heard, okay? Especially for everyone at home, right? All right. Conceptually quite interesting, I think. Just let that sink in for a minute. You're going along a curve, maybe you're pushing a mass along a curve or a line. You start at one point, you end up at another point. It doesn't matter which way you go if you have a situation like this. You're still using the same, you'll still get the same answer, the same result. That is huge. Like, that's crazy, right? It's intuitive. It's not intuitive. All right. Okay, let's do another one, because this is quite fun. Okay? All right. I've summarized it up there. It's called the fundamental theorem of line integrals. It's good. You should use it whenever you can. You should use it whenever you can. But let's do the second exercise here. I think the answer here should be 6 and not 3. Okay? When I put these notes together, I asked 2 of my colleagues to check everything, and I've found about 5 mistakes so far. Right? They didn't do any work. I even listed them in the opening page, like, "Thanks to this person, you did no work." The truth comes out. Okay, so let's play a little game. Find a phi such that the gradient is our vector field. Okay, it's a competition now. Little game, almost as good as noughts and crosses, but I can't promise. What would a phi be?
X, Y, Z.
Oh, yeah, you wrote it down in one line. Okay, let's try it. Because sometimes you can guess, guess and check. All right, let's try it. So if I take the gradient of that, the first term's going to be yz, second term's going to be xz, third term's going to be xy. Okay? Is that what we've got? Yep. Sounds pretty good. Okay? So what does that mean in terms of computing this integral? Let's look at the question. Compute the line integral from that point to that point where C is any path. Oh, mind blown. Right? You choose any path. You choose. Okay, it could be a straight line, any path, whatever. Okay? So that's the point A, that's the point B. Right? Let's do it. Okay, so x equals 2, y equals 1, z equals 3. 2 times 1 times 3. Boom. That's it. No derivatives needed. No parameterization needed. No dot product needed. You know, feel like one of those infomercials. Can't you make it cheaper? Can't you make it simpler? This is pretty simple, right? There's a lot of interesting ideas going on here, but from a calculation point of view, would you rather do this or that? Right? Work smarter, not harder. Okay? Now, can you do this for every problem? No, not necessarily. Sometimes you'll get problems where you just can't find the phi because the phi doesn't exist or it's really hard to calculate. Okay? Questions? Will you see something like this in your lab test? Maybe. I'll have to check the questions.
How do you know if the phi doesn't exist?
Yeah, so for irrotational fields, it's a sufficient condition. Okay, so it's sufficient. I don't think it's necessary, right? So if the vector field's irrotational, then you definitely know that there's a phi that exists, right? That's the sort of connection here. If the curl is not 0, you don't know. Okay. You don't know. Maybe it exists, maybe it doesn't. But what you can do if you're unsure, right? If you're unsure, you can go. Oh, I've just written it out here. Yeah. This is just my working. You can go to these three equations and try to solve them. Right? Now, sometimes it'll be clear, oh, I can't solve that. Or it's not possible to solve that. Okay? That's like, okay, try something else. Yeah.
Like in terms of just like, I guess, exam strategy or practice, would you recommend checking the cross product or like the curl first or jump straight into trying to solve the...
Yeah, it's a good question, really good question. Okay, I would read the question because I think with some of these problems, they want you to use this fundamental theorem. Okay, so that's like my first thing. Okay, I'm going to read the question. Do you want me to do it this way or whatever? Are you leading me in some direction? Whatever. If you're quick with calculating the curl, why not? You know, why not? It's up to you. Okay. I mean, with this one, we didn't even check it. We didn't even check the curl here, right? We just integrated it because we could. Okay, very good questions. Okay, how's everyone going at home? 26 people. Let us know what you're thinking at home about this. Like, conceptually, this is amazing, but also from a time-saving perspective, it's huge. It is huge. Okay, the limitation is you can't use it all the time. Okay, you can't use it all the time, which sucks. All right. Okay. So this is the last case study in chapter 3. So there won't be anything more on lab test 1 past today's, if I finish, which I should, past today's lecture. So that means you've got at least 1 week to memorize all the questions for lab test 1. No, don't memorize. Don't memorize. Okay? So next week, I want everyone, like maybe, should we do some revision next week? Something like that? Who would like some revision next week? Who's like, nah, 0 flux given? Okay. I've been saving that one up. Let's do some next week then. Maybe on Friday. We can do some Friday afternoon. Okay. So when I introduced gradient, divergence, curl, I gave some sort of broad physical interpretations, right? So with gradient, we're talking about normal vectors to level curves and level surfaces. With divergence, we're talking spread. Yeah, we're talking spread. With curl, what are we talking about? Rotation. Rotation. So let's have a look at flux. So what is flux? What is flux? Everything okay? No? Huh? Are you in the next class or are you in ours? Oh, you're in the next one. Okay, you're just visiting. Okay. Flux is a fancy Latin word that's connected with the idea of flow or flow rate, rate of flow. Okay? And what we can do is look at how, say, a fluid flows over a surface or a curve. Okay? So let's have a look at the example and it'll become clearer. So you've got an ellipse. Calculate an outward pointing normal vector. And here's the vector field. Compute the outward flux. What does that even mean? So let's start with a picture and see what we can do. All right, so this is going to be our curve C. All right, so we're in the xy plane. And that's going to be our ellipse. Okay, compute an outward normal vector, n, to C. Okay, so outward means it's sort of not pointing to the interior, I guess. But there's a couple of ways of doing that. One way is to use the gradient vector, right? So on YouTube, I use cross products. I think I looked at it the other day. I think gradient vector is just as good, and it's quicker. Okay, so let's parameterize the ellipse. So x can be 2 cos t, y can be sine t. I think that's what I've got. Yep. Okay. So I'll go up here, that's my r vector, and there's a point. Okay? All right. Compute an outward pointing normal. All right, so there's a couple of ways of doing that. One way is to compute the tangent vector and then cross it with something. But another way is just to use the gradient. Okay, so if I say, oh, my function's going to be x squared on 4 plus y squared, and I'll consider that just at equal to 1, I can compute the gradient. Okay, so let's do that. A couple of ways you can do it. You can sort of differentiate that first and then put in your parameterization. I'll do it the other way. I'll sort of reverse it. Is that what I've done? Hang on a second. Just give me a sec. Okay, I'm going to take the gradient of f and I'm going to evaluate that on my curve. Okay, so let's take the gradient. So it's going to be x on 2, 2y, and I want that on c. So I'm going to replace x with 2 cos t, y with sin t. Okay. So that is going to be a normal vector. But if you look carefully at part A, compute an outward pointing normal vector, great. What I'm going to do for part B is not use that just any old outward pointing normal vector. I'm going to normalize it. Why? Because it gives us definiteness with our answer. Okay? We can think about the flow per unit something, right? So let's do a unit vector. Oops. Okay, so I've got this and this. So the length of that's going to be square root cos squared plus 4 sine squared. Okay, so that is an outward pointing normal vector that has length 1. All right, so what are we going to do with it? Well, I'm glad you asked. We're going to look at this. Okay, now, before we do any more calculations, let's think about this. The dot product of f with the unit normal vector. Okay? Okay, so let's get a little bit conceptual for a second. The unit normal vector, so it might look something like this, right? It might be like just in here. All right, so who can tell me what does that bottom line kind of represent? How would you explain it? Yes.
Directional derivative?
Oh, close, not quite. So close, I guess I'm thinking more geometric. So not a bad guess, but not quite, not quite. So directional derivative definitely uses a dot product. So, you know, that's how we compute it, but it's slightly different. What we are computing here, okay, let's say that's my vector field. Yeah. Draw a little right angle triangle. It's the component of the vector field in the normal direction. moving out of the curve. Okay? Let me say that again. It's the component of the vector field that points in the same direction as the normal vector. So that kind of gives you an idea that that's how sort of, I'll move my thing. That kind of gives you an idea of, so there's my F. Just say at that point, there's my N, I draw a little right angle triangle. The component of the vector in that direction can be captured by the dot product. Okay? So it's like an alignment thing. So that's why we're talking about outward flux. It sort of gives you an idea of how much the tendency is of the vector field to push out over the boundary, over the edge. Okay? Okay, so let's just compute it and see what happens. So we've got this dotted with this, yeah? Oh, hang on, no. So F of R of t. Okay, so x equals 2 cos t, so that's going to be 8 cos ti. Y equals sine t, that's going to be just sine tj. Okay, so bring together this and our unit normal vector, which is this. It looks like we've got a mess, but things are going to simplify. So it's going to be, so that times that plus that times that. Okay, so now let's integrate that as a line integral. Okay, this is the last step. Okay, so we're going to just integrate this expression. So what is the length of the derivative? So r's up there. The derivative is going to be, squish that in. Okay, so we're going to look at the length of that. Okay, so there it is. Okay. Now, what is the length of that? It's going to be, oh, sorry, there should be a sign there. That's sign. Okay, so it's going to be exactly that. Okay, so we get a cancel. And now we just integrate. So let's call it f of, let's call it flux. So it's still a line integral. We've just changed it because we're interested in the sort of outward normalness of what's going on. That's why we've introduced that unit vector. Okay? But let's just look at our answer for a second. It's a positive answer, 10 pi somethings, right? It'd be maybe, I don't know, volume per unit time or something like that. You would expect that with a positive answer that there's a net outflow going from the inside of the ellipse through the boundary to the outside. Okay? Yeah. So I'll just move that back up. Yep, 10 pi. All right, so just for people at home, oh, shut up. Yeah. So, great theorem. It is a great theorem. The fundamental theorem of line integrals is amazing. And the final example, I've just sort of given you an idea of how you can use line integrals to talk about flow rates or fluxes or net flow or inflow and outflow, those sorts of things. Okay? So, yeah, look, this is a pretty cool example. I'm going to be honest, I'm not going to lie, right? And it brings together all the stuff that you learnt in vectors, basically, last year. Dot products, unit vectors, right? And it brings them with a calculus connection, this vector calculus that we're learning at the moment. Okay, so being able to visualize dot products, you know, someone mentioned projection before, right? Someone mentioned projection. It's really important.
Could you please re-explain the second consideration?
What's the second? Which one's that? Which one's that? Yeah. Okay, good question. So where? Okay, good question. So where does this thing come from? I'm glad you asked. Okay, if we go back to see how it's there? Huh? It's the length of a tangent vector to the curve. Yep. Yeah. So we're basically inserting that there in the third bottom line so we can connect it with line integrals that we know how to compute. Okay? Yep. Other questions? All right. Well, have a great day, everyone. There's about 5 minutes for consultation if anybody wants to come down. But the most important thing, go and have a look at Mobius Lab Test 1 practice questions. You have all the power now to do it. Okay, there's nothing more in lectures, but we will do some revision next week and maybe on Friday. So have a great week, and I will see you on Friday, hopefully.